Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 3 today on numeration systems and whole number operations. So today we're going to be looking at addition of whole numbers, which includes number relationships, including comparing and ordering, the meaning of addition by studying various models, properties of addition and how to use them, addition algorithms, including the standard algorithm, and how to use them to solve problems, addition with number bases other than 10, and mental addition computational skills and estimation. So one addition model is called the set model. A set model is one way to represent addition of whole numbers. Suppose Jane has 4 blocks in one pile and 3 in another. If she combines the two groups, how many objects are there in the combined group? So recently we were looking at sets. So if you think of the group of 4 blocks as a set with 4 elements, the number of elements in that set is 4. And then the group of 3 blocks is a separate set with 3 elements. If you combine those sets, which is taking the union, you end up with 7 elements. Now notice, in order for this to work, the sets have to be disjoint. Remember, that means they have no elements in common. So the definition of addition of whole numbers using sets is let A and B be 2 disjoint finite sets if the number of elements in set A is the number A and the number of elements in set B is the number B. Then the definition of A plus B is the number of elements in the set A union B. Another model for addition is the number line model. Kenzo has 4 feet of red ribbon and 3 feet of white ribbon. How many feet of ribbon does he have altogether? Or another example is, one day Laura drank 4 ounces of orange juice in the morning and 3 ounces at lunchtime. If she drank no other orange juice that day, how many ounces of orange juice did she drink for the entire day? So notice that these are just 2 different examples of 4 plus 3. So a number line model for either of those problems would look like this. You start at 0 and draw an arrow with length 4, which of course will end at 4. And then you draw another arrow starting at the 4 with a length of 3. And when you combine those 2 arrows into the red arrow you see here, the answer to the addition problem is at the end of the long arrow. Students need to understand that the sum represented by any 2 directed arrows can be found by placing the endpoint of the first directed arrow at 0 and then joining it to the directed arrow for the second number with no gaps or overlaps. So just like you saw in the previous example. The sum of the numbers can then be read. All right, definition of less than using addition. For any whole numbers A and B, A is less than B, which of course is written like this, if and only if there exists a natural number K such that A plus K is equal to B. So for example, we can say that 5 is less than 7 because there is a natural number, namely 2, that makes 5 plus 2 equal 7. Remember that A is less than or equal to B means that either A is less than B or A equals B. And remember that A is greater than B means the same thing as B is less than A. All right, counting on. The strategy of counting on is an addition strategy where addition is performed by counting on from one of the numbers. For example, 5 plus 3 can be computed by starting at 5 and then counting 6, 7, 8. So this is kind of like adding numbers on your fingers, right? The addition 7 plus 4 can be performed by starting at 7 and counting 8, 9, 10, 11. And then doubles. Use of doubles, such as 3 plus 3, receive special attention. After students master doubles, doubles plus 1 and doubles plus 2 can be learned easily. For example, if a student knows 6 plus 6 equals 12, then using the associative property, 6 plus 7 can be thought of as 6 plus 1, which is 1 more than the double of 6. So that gives you 13. Another strategy is that of making 10 and then adding any remaining. One way is to use 10 frames to make a 10. So for example, 8 plus 5, start with 8 plus 2, which gives you 10, and then you have 3 remaining. That'll bring you up to 13. All right, whole number addition properties. The closure property of addition of whole numbers says that if A and B are whole numbers, then A plus B is a unique whole number. So that says two different things. First of all, it says that A plus B is a whole number. And it says the word unique tells you that there's only one answer. So you might appreciate this a little bit more if I give you an example of something that does not have the closure property. Subtraction of whole numbers does not have the closure property. So for example, 2 and 5 are both whole numbers, but 2 minus 5 is not a whole number, right? 2 minus 5 is -3. -3 is an integer. It is not a whole number. But when you add two whole numbers, you always get a whole number, and you always get one specific whole number, right? You don't get two different ones. The closure property implies that the sum of two whole numbers exists as a whole number, and that the sum is a unique whole number. For example, 5 plus 2 is a unique whole number, 7. Commutative property, and you see here a couple of different ways to illustrate it. If A plus B, if A and B are any whole numbers, then A plus B is the same thing as B plus A. So this is a really, really useful property for students who are learning their addition facts. You know, if you're trying to learn all of your addition facts for numbers, let's say 0 through 9, this cuts your work roughly in half, right? Because if you already know 8 plus 3, then automatically you know 3 plus 8. So you can demonstrate this using a number line model, like you see here. 3 plus 5 gives you the same answer as 5 plus 3, or you can demonstrate it with these blocks. The associative property of addition of whole numbers says that if A, B, and C are any whole numbers, then the sum of A plus B and C is the same as the sum of A and B plus C. And we're going to be making use of this later, all right? So that is also a useful property. The identity property of addition of whole numbers. There is a unique whole number 0. By the way, this is why we're working in whole numbers and not natural numbers, because 0 is not a natural number. 0 is called the additive identity, and the special property of 0 is that for any whole number A plus 0 and 0 plus A are both equal to A. In other words, if you add 0 to any whole number, you just get that same whole number back. All right, which properties of whole numbers are illustrated in each of the following statements? Starting with 6 plus 8 equals 8 plus 6. So think about the properties that we just talked about. Try to remember which one this is. Which one says 6 plus 8 equals 8 plus 6? That is called the commutative property of addition. Next, which property says that 1001 plus 834 is a unique whole number? That was the closure property of addition. Okay, this one's a little tricky. Which property says that the sum of 3 plus 6 and 9 is the same as the sum of 6 plus 3 and 9. This is one of my favorite examples. I use this one all the time. It kind of looks like the associative property, right, because of the parentheses. However, the only difference between this and this is that the 3 plus 6 has been changed to 6 plus 3. So this is actually just the commutative property again. All right, which property or properties say that the sum of 8 plus 5 and 2 is the same as the sum of 2 and 8 plus 5? Okay, so that part might be one property. And then that the sum of 2 and 8 plus 5 is the same as the sum of 2 plus 8 and 5. Okay, well, this one here, the first equality, is the commutative property. All they've done is switch the 8 plus 5 and the 2. So they have not moved any parentheses around. So that one is commutative property. However, the second one, they've left the numbers 2, 8, and 5 in the same order, and they just moved the parentheses to be around 2 plus 8. That one is associative. So this is actually both commutative and associative. All right, some addition algorithms. First, we have the concrete model. So we're using base 10 blocks to illustrate 14 plus 23 equals 37. Remember that 14 can be modeled using 1 long and 4 units, and 23 can be demonstrated using 2 longs and 3 units. So when you put all your longs together and all your units together, you get a model for 37. The expanded algorithm, we start with adding 4 plus 3, which is 7. And then we add 1 plus 2 is 3. Now remember, the 1 and the 2 are in the tens place. So that 3 has to go in this column. And it's good to put a 0 over here as a placeholder. All right, so when I add my 1s, I get 7. When I add my 10s, I get 30. The sum is 37. Okay. Now the standard algorithm works very well for this problem, especially because there's no carrying or regrouping. However, in a problem like this, I think that the expanded algorithm actually makes a lot of sense. You do 7 plus 8 is 15, and then 3 plus 2 is 5. Remember, that means 5 tens, which is 50, and then 15 plus 50 is 65. Standard algorithm with regrouping, this is what I learned when I was in school. 7 plus 5 is 15. Add the 1s and regroup. So put that 110 over here. 1 plus 3 plus 2 is 6. So that gives you 65. All right, adding 2 3-digit numbers with 2 regroupings. So I'm going to talk you through this. The problem is 186 plus 127. So the first thing we're going to do is add the 1s. We're adding 6 plus 7. You see the 6 plus 7 over here. So gather up 10 of these and trade them in for a long. So that's going to leave you with 1 long and 3 units, which is 13. So we take the 3 and carry the 1. That 1 should actually be over here. Now we'll add the 10s. So we have 8 10s. We have the 110 that we got in the previous step from regrouping. And then we have the 8 10s from 186, and we have 2 10s from 127. So notice they're taking the 8 plus 2 10s, which adds up to 10, and trading that in for a flat, which remember represents 100. So you add all these longs together and you get 1 flat and 1 long. So here is the 1, carry another 1. And then finally we'll add our hundreds, which are represented by flats. And that comes out to 3. So the answer to 186 plus 127 is 313. All right, another algorithm for addition is partial sums, the left to right algorithm for addition. Um, this is really similar to what we looked at a little while ago, the expanded algorithm. The only difference is it's being done left to right. So for example, to add 568 and 757, you can start by adding the hundreds. 500 plus 700 is 1200, then add the tens. 60 plus 50 is 110, and then add the ones. 8 plus 7 is 15, and then add those all together. All right, I personally really like the lattice algorithm. We're also going to look at this for multiplication. So this is one I definitely need to explain. So we're adding 3,567 and 5,678. So 7 plus 8 is 15. This kind of diagram here is called a lattice. 7 plus 8 is 15. 6 plus 7 is 13. 5 plus 6 is 11. 3 plus 5 is 8. And then to get these numbers on the bottom, you add diagonally, going this way. So 5 is just 5. 1 plus 3 is 4. 1 plus 1 is 2. 1 plus 8 is 9. Column addition. In the column addition algorithm, we add the numbers in each column, writing each sum directly beneath the column. Then we regroup each place one column at a time. Base 10 blocks are often used in the column addition algorithm. The opposite change algorithm, we decide which addend is closer to a nice number, typically 10 or a multiple of 10, then decide how to adjust that addend so that it ends in one or more zeros, and adjust the other addend the opposite way. The goal is to make the addition problem a problem without the need to regroup. And I thought you could stand to see a couple of examples of this. So in the first example, we're adding 364 plus 278. Notice that 278 is very close to 280. So we're going to bump that up to, and then bump the other number down to. So this gives you a problem that's slightly easier. But we can make it even better if we take this 280 and bump it up to 300 by adding 20, which means we have to make up for that by taking 362 and subtracting 20. So instead of adding 364 plus 278, you add 342 plus 300, which is a much simpler problem. Another example is 5,261 plus 9,400. Subtract 400 from 9,400 to get 9,000, and then add 400 to this number, and it gives you a much simpler addition problem. All right, in the scratch algorithm, you add the numbers in the units place starting at the top. When the sum is 10 or more, record this sum by scratching a line through the last digit added and writing the number of units next to the scratch digit. So let's look at this problem. 87 plus 65 plus 49. We're going to start by adding 7 plus 5 is 12. Since that's more than 10, we're going to scratch out the 5 and put a 2 for the ones in the sum 12. Then we're going to go 2 plus 9 is 11, and since that's also more than 10, we're going to scratch out the 9 and put a 1 there. Continue adding the units, including any new digits written down. When the addition again results in a sum of 10 or more, repeat the process. Okay, so now, when the first column of additions is completed, write the number of units, 1, below the addition line in the proper place value position. So in this case, it's ones. Count the number of scratches, which is 2, and add this number to the second column. Because remember, each time we scratched out a digit, we were taking out a group of 10. So we're putting those groups of 10 over here. And then we add these together the tens place. 2 plus 8 is 10. So we scratch the 8 and just put a 0. 0 plus 6 is 6. 6 plus 4 is 10. So we're going to put this 0 here. And since there were 2 scratches in this column, and we don't have any other numbers in the hundreds place here, we just put that 2 down here. All right, this is something that I really enjoy. Understanding an addition in bases other than 10. So we're going to look at base 5. I've always felt that this is a really useful thing to do in a class like this, because remember, when you're teaching elementary school, your students are not any more familiar with base 10 than you are with base 5, okay? So it really allows you to get inside their heads, all right? So the first thing that you would need before you do this kind of addition, you would need a base 5 addition table. So let me explain this for a minute. Even in base 5, 0 plus 0 is 0. Hold that thought. I mentioned to you a little while back that I like to think of base 5 as pennies, nickels, and quarters, all right? So we're going to imagine that we're adding pennies here, and every time we get a group of 5 pennies, we're going to trade it in for a nickel. So 0 pennies plus 0 pennies is still 0 pennies, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4. No problem at all until you get to 1 penny plus 4 pennies equals, thinking in base 10, equals 5 pennies, but we're going to trade in those 5 pennies for a nickel. So this 1 0 that you see here stands for 1 nickel and 0 pennies, okay? 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4. 2 pennies plus 3 pennies is 1 nickel and 0 pennies. 2 pennies plus 4 pennies is 1 nickel and 1 penny, etc., etc. Okay, so hopefully you got the idea. We're going to use this addition table to add 144 in base 5 plus 34 in base 5. So we start by adding 4 plus 4. From the addition table, 4 plus 4 is 13. So we're going to put, and we're using the expanded algorithm, we're not going to carry. Okay, 4 plus 4 is 13. Next, we're going to do 4 plus 3. 4 plus 3 is 12. Don't forget to put a 0 here. So this would be like 4 nickels plus 3 nickels. I would take 5 of those nickels and trade them in for a quarter. So think of this 1, 2, 0 as 1 quarter, 2 nickels, and 0 pennies. And then finally, just bring down the 1. All right, and then add all these numbers going down. So 1 quarter plus 1 quarter is 2 quarters. 1 nickel plus 2 nickels is 3 nickels. 3 pennies is 3 pennies. So 144 in base 5 plus 34 in base 5 equals 233 in base 5. Or you can do it with traditional, regrouping and carrying. Okay, very similar to what you saw over here. All right, that brings us to mental mathematics and estimation for whole number operations. Mental mathematics is the process of producing an answer to a computation without using computational aids. So this used to be a lot more important when, everybody wasn't walking around with a calculator in their pocket. This has kind of become sort of a lost art. All right. Computational estimation is the process of forming an approximate answer to a numerical problem. All right, so a few mental mathematics tricks, starting with adding from the left. So to add 76 plus 25, by the way, we're in mental mathematics right now, so we'll be getting exact answers. We're not into estimation yet. 70 plus 20 is 90, 6 plus 5 is 11, and then just add 90 plus 11 is 101. So a couple of our algorithms worked like that. Breaking up and bridging, this is one that I catch myself using sometimes. Add the first number, 76, to just the tens in the second number. So do 76 plus 20 is 96, and then add that sum to the units in the second number. 96 plus 5 is 101. Another mental mathematics trick is trading off. So take 76, this is kind of similar to the opposite change algorithm, right? So to make this into an easier problem, 76 plus 25, you add 4 to 76 to get 80, and then make up for that by subtracting 4 from 25, that gives you 21. So instead of doing 76 plus 25, you do 80 plus 21, which is 101. Using compatible numbers. Compatible numbers are numbers whose sums are easy to calculate mentally. So here I'm trying to add 130 plus 50 plus 70 plus 20 plus 50. I'm going to group those numbers together so that they come out to nice numbers like 200 or 100. 130 plus 70 is 200. 50 plus 50 is 100. That just leaves me with the 20. So I do this as 200 plus 100 plus 20, which comes out to 320. Making compatible numbers. You can take 75 plus 25, which is 100, and then just add the 1 that you left out to get 101. All right, computational estimation. So this is when it's not super important to get an exact answer. So one example is front end with adjustment. Add your front end digits. 4 plus 5 plus 2 is 11, which means 1100. And then just make the adjustment. 22 plus 31 is about 50. 74 is about 70. 50 plus 70 is 120. And then add those two numbers together. The estimated sum is 1,220. Grouping to nice numbers. So here I'm trying to add a whole bunch of numbers together. So you just look for numbers that add up to approximately add up to nice numbers. So for example, 39 plus 64 is about 100. 23 plus 32 plus 49 is about 100. So this sum is approximately 200. Clustering is used when a group of numbers clusters around a common value. In this case, these numbers are clustering around 5,000. So the average of these numbers is about 5,000. So instead of trying to add those numbers together, just say, well, each number is about, well, it's not that each number is about 5,000, but because the average is about 5,000, this sum should be very close to 5 times 5,000. See, some of them are under 5,000, some of them are over 5,000. So an approximate sum of these 5 numbers is 25,000. And then, of course, you can just use rounding. So in this case, we're rounding each number to the nearest thousand. And that tells me that 7,262 minus 3,806 is approximately 3,000. Or you can use the range. So here is the original problem. If you round each number down, you get an estimated sum of 10,000. If you round each number up, you get an estimated sum of 12,000. So the sum is somewhere between 10,000 and 12,000. And that's going to do it for section 3.2. We will see you next time.